I'm going to begin. Hey everyone, welcome back to multimodal machine learning. Today I'm going to talk more about reinforcement learning and really wrap up some of the ideas in generative models that we've talked about last Thursday. So if you recall, last Thursday we started with these deep generative models. We've talked about their applications in image generation, and we left out this part of applying them to text generation. So today we're going to wrap up reinforcement learning and then also link back to how we can do generation of text, which are these discrete tokens. And we're going to use some ideas from reinforcement learning to actually help us do text generation. So just some admin stuff first. The instructions for the midterm reports and also midterm presentations are on Piazza. So recall that you first have to do a pre-recorded presentation, and that's due on Friday, November 13th. That's in about 2 weeks. And you also have to write up a midterm report, and that's also due in 2 weeks on about November 15th. So just make sure you start working on both of these midterm assignments right now and not leave it until the last minute. The whole goal of the midterm report is to implement some of these multimodal baselines for your problems and really do some error analysis of these multimodal baselines and really go more in depth into your proposed ideas. Also, LP made this post about there being wildcards for readings as well. So we've already announced that there are wildcards for your project assignments. So those are free 24-hour extensions for either your proposal, midterm, or final reports. And we're also introducing it for your reading assignments. So I think each student gets one wildcard that can extend one of the reading assignments by up to 24 hours. So make sure you check out details on Piazza. And also recall that, whenever we're giving lectures, just feel free to type up your questions either on the chat here. I'll be looking at it live, and also type up questions on Piazza. And other TAs will be following up on Piazza about these questions. So let's begin. For today's lecture, again, some acknowledgements from the deep Rrl courses at Berkeley and CMU. Again, I'm going to go through at a really high level this introduction to reinforcement learning and really focus on the multimodal applications. But if you really want to go more in depth, I would encourage you to check out these semester-long courses at other universities. So just a quick recap. Last week, we kind of looked at the reinforcement learning problem. We looked at an agent who is situated in some environment, and this agent continuously starts in some state and take actions and observe rewards and go to next states within this environment. So this sequence of state, action, and rewards is known as its trajectory. We also looked at this formalism of reinforcement learning, being that there being a set of states S in which the agent could be in, a set of actions A, which an agent will start sampling actions from, as well as a transition function, which tells you, given a particular state and a particular action, what is the distribution of next states that the agent could end up in. And also this reward function. So given a particular state and taking an action and going into a particular next state, what is the reward returned by the environment? The agent is in some start state at the beginning. And the goal of reinforcement learning is to maximize these cumulative discounted rewards across a really long-term period, across a horizon H. And we've seen how this Markov decision process of an agent being in some environment really encapsulates many of the broad applications of real-world reinforcement learning. So that includes a robot being an agent situated in some environment in which it has to explore, and also in multi-agent reinforcement learning settings where there's multiple agents, in this case, 22 players playing soccer, situated in some environment and trying to maximize rewards of scoring a goal. So this general reinforcement learning and these Markov decision processes are really broad ways of encapsulating these tasks. All right. So we looked at in reinforcement learning, the goal is to maximize this cumulative long-term reward. So at a particular time step, we denote that as G of t. And what that's equal to is the reward at the next time step, that's your immediate reward, as well as rewards into the future. And we've seen that we want to discount these rewards into the future by a factor gamma, which is called a discount factor. And the goal of this discount factor gamma is to make sure that both empirically and theoretically, you can actually build policies and converge. And it's also borrowed from this idea in economics that money you have now is more valuable than money that you might have in the future. So the goal is to maximize this set of long-term total discounted rewards. And that's where the main difference from supervised learning is, right? In supervised learning, you just care about an immediate reward, but in reinforcement learning, you care about this long-term discounted rewards. And again, just to recap, a discount factor close to 0, which means that all the rewards in the future are discounted to be 0, and you care more about rewards in the immediate short term. And on the other hand, this large values of the discount factor gamma close to 1 means that you care more about long-term rewards, possibly at the expense of short-term rewards. And the whole goal of reinforcement learning is to learn a policy. And a policy describes a distribution over actions given a particular state, pi of a given s, which basically tells you, for all states that the agent could possibly be in, what is the distribution of actions that I should take in order to maximize my long-term cumulative reward. So here is the slide that summarizes everything. An agent in some environment, the important terms in the MDP, the goal of reinforcement learning, which is to find the best policy, take an argmax over all policies that maximizes the expected long-term reward following action under this policy. And we also looked on Tuesday, the main differences between reinforcement learning and supervised learning. The fact that reinforcement learning involves making sequential decisions, which allows you to look at cumulative rewards, while supervised learning only looks at one-step decisions and maximizing immediate reward. In reinforcement learning, we also run into this issue of sparse rewards. So that means taking multiple actions across a very long horizon, only observing very sparse rewards at the end. But you don't get that in supervised learning, because in supervised learning, for every prediction that you take, you have a dense reward. And sometimes in reinforcement learning, the environment may be unknown. So in case of Markov decision processes, not knowing the transition probabilities, but in supervised learning, the environment, which is your set of predictions, are always known. So just to quickly recap last week, on Tuesday, we looked at the first case where if we had a fully known Markov decision processes, where we could enumerate all states, we knew the transitions, and we knew the rewards, we derived this set of Bellman optimality and Bellman expectation equations. Essentially, these are equations regarding Q star or Q pi. So what Q star would mean is given a particular state and taking a particular action, under the optimal policy, what is my expected long-term reward? And for V star, so that will be given a state, and for taking the optimal policy, what is the long-term expected reward starting from that state? So these are the values of the Markov decision process that you want to calculate. And we show that we could derive using equations these exact optimality equations of relating your Q stars for a particular state in action with your Q stars for other states and other actions into the future. And we could therefore optimize our Q stars in order to respect this optimality equation. If you're working with your optimality equations, it's called Q value iteration and value iteration. If you're working with expectation equations, that means computing Q of pi or V of pi of a specific policy, that'll be called Q policy or policy iteration. So we showed that at least in these simple cases where you could fully enumerate these states, compute this expectation with respect to your transitions exactly, you're guaranteed to converge to the optimal policy. But in the real world, you don't actually have these assumptions. This only works for small and discrete state and action spaces. So it doesn't really work for high-dimensional states being images and actions being continuous. And likewise, it requires known transitions in the Markov decision process, which you don't get in the real world. So to relax that assumption, we looked at MDPs with unknown transitions. So we went from Bellman optimality equations to actually replacing these true expectations over your next states with just approximate expectation. In other words, samples of next states. So in other words, when you're in a state and a particular action, you would just give that to the environment and see what the environment returns you as its next state without knowing the exact transitions. And we saw here that this idea of exploring the environment is important to use an epsilon greedy method. So in other words, leave epsilon probability of you exploring in the environment randomly instead of depending completely on your current policy, because your current policies are not good. And again, once you replace this expectation by samples, you would like to solve for your Q stars that respect this Bellman optimality equation. And what you would do is that you would treat the right-hand side as a target and the left-hand side as the old estimate, compute the difference, and you want to minimize this difference to 0. Again, the issues are that you will have to keep all your Qs of S and A separately. So in other words, you will keep a table that has number of S rows and number of actions columns. So still requires small and discrete state and action spaces, although now you do not need to use the true transition probabilities to compute the expectation, but rather using samples. So the next question is, how can we generalize this to even work with unseen states and large and continuous state and action spaces? So that's when we extended tabular Q-learning to deep Q-learning, which is the idea that instead of keeping a table of your Qs across all states and actions, I would like to amortize it, but just learning a single weight function, a set of neural network parameters in practice that takes in a state and predicts your QSAs for all possible actions. So the benefit here is that just because you have really powerful function approximators, if you've trained your model for a particular state to predict its QSAs for a very similar state, you can also apply it through your function approximation and get similar realistic values of your QSAs. So now it works for unseen states. And by good choice of your function approximation, be it convolutional networks or recurrent models and transformers, you can also work with high-dimensional state spaces such as images and text. But the ideas, the optimization has the same ideas, which is to treat the right-hand side as a target and the left-hand side as the previous estimate. We know that at optimality, these Q stars on the left and right-hand side should be equal. So what you can do is take the difference and try to minimize that to 0 using gradient descent. We saw that this naive method might have some issues with correlated samples and non-stationary targets. And we also looked at how we can alleviate some of these issues by using these replay buffers, experience replay buffers, and sampling a mini batch of transitions that are not correlated with each other. And to remove the problem of non-stationary targets, you will keep one set of weights fixed. So at least your targets that you're trying to match are fixed, and you're only updating the weights as given by your predictions, and only replace these previous weights W minus with your latest set of weights every 1,000 iterations. So all of these were done on Tuesday. So this is just a very quick recap of what we've done. And using these ideas of gradient descent plus exploration, epsilon greedy exploration plus experience replay and fixed Q targets, this actually works for high-dimensional state and action spaces and also generalizes to unseen states. And we've seen how this can work for these games, including like Atari games, where we have these images as states. So recall, all we've done so far, we've looked at three methods of basically estimating our Q stars, right? We started with these policy and value iteration to solve them exactly. We've looked at Q learning to solve them approximately, and deep Q learning, which further involves deep networks. All of this was to find your Q stars, which is the action value function for a particular state and action. So if we have these Q stars, we know that we can obtain the optimal policies using epsilon greedy. So if the action satisfies the argmax over all actions, then you would take that with really high probability, and otherwise you would take maybe very small, otherwise small probability of random actions. And likewise, the other method was to solve for your V star, right? So V star would be a value iteration. And likewise, we can relate our Q stars and V stars. And again, if we solve for V star, what we can do is we can also obtain the optimal policy, but now you have to do one step look ahead. So in other words, given a state, I'm going to take a max over possible actions. And for each action, I'm going to compute an expectation over possible next states, the reward that you obtain, and the optimal value function for the next state. So that allows us to compute the utility of each action, and the action that satisfies the argmax would be the action that's taken by the optimal policy. So all of the methods we've talked about on Tuesday were to find these Q stars and V stars as an intermediate step before we actually obtain the optimal policies, which is the one that we care about. So in today's lectures, we're actually going to give an alternative perspective on reinforcement learning. Instead of optimizing for our value functions, our Q stars and V stars, and then inferring the policy, we're going to try to optimize for the policy directly. So we're going to forget all of these Q stars and V stars. We're going to forget MDPs, and we're just going to optimize for this policy directly. And we're going to see whether we can derive some good algorithms for that. And afterwards, we're going to look at this set of algorithms called active critic methods, which kind of combine last week's Tuesday's lectures and today's lecture. And then we're going to look at some applications. So again, on Tuesday, we look at all these state value functions and action value functions, your V's and Q's. And after we obtain these optimal V's and Q's, we then derive the policy. This is in general called value-based RL, named for the fact that we are trying to derive these optimal state and action value functions. And the other perspective of RL is called a policy-based RL. So in other words, we're going to forget these value functions, our Q's and V's, completely, and instead just directly learn a policy. So what would that look like? So a policy would take in a state and it would try to output some set of actions. In other words, given state, it will try to output a distribution over all actions that you can take. And in general, we're going to assume that we have a set of parametrized policies that are given a state, in this case, an image, go through a bunch of neural network parameters data and outputs a distribution over your actions. So in this case, you just have this paddle moving up and down. So you will just have one output neuron that represents the probability of moving up, and 1 minus the value of that neuron would be the probability of moving down. So you see, in this case, you have nothing about Q's and V's, and you're just directly parametrizing a policy from states to actions through a set of parameters data. So why do we want to do this? So there's a couple of reasons. One reason is that often your policy pi can be simpler than Q's and V's. So consider the case of training a robot arm to kind of pick up some objects, right? So if you want to really define a Markov decision process for a robot arm picking up these objects, you possibly have to define all your state as all possible parameters in the robot hand. So all possible parameters across all possible joints that a robot hand contains. So your QSAs and your V of S could be very high dimensional. But your policy, instead, it could abstract across all of these very low dimensional states, very fine grained states, and just define some high level semantic policies, such as open or close your hand. So you could possibly train a model that just has two output neurons, one, the probability of opening a hand, and two, the probability of closing a hand. So this is an example of your policy being simpler than the Q's and V's across your Markov decision process. Another issue is that for both your V's and Q's, once you compute them, you have to do one more step before you actually derive your optimal policy. So this works, we saw that for V stars, you have to do one step look ahead. And sometimes this one step look ahead is hard if you have a very large number of possible next states that you could transition to. Sometimes computing this expectation might be difficult. And likewise, even if computing this one step look ahead is not difficult, you do need an argmax over your actions before you can get the best possible policy. And that presents a challenge for continuous and high dimensional action spaces. You might not be able to do this argmax over your actions very easily. So sometimes it makes more sense to directly optimize for a policy instead of computing these Q stars and V stars before obtaining a policy. So that is the main motivation of today's lectures. On Tuesday, we looked at value-based methods. Today, we're going to go into policy-based methods, which directly learns a policy. And then at the end of the lecture, we're also going to look at this set of methods called actor critic, which really combines the best of both worlds. So obviously, since there's two branches of methods in RL, value-based and policy-based, there must be some trade-offs, right? So there's some both conceptual and empirical trade-offs. Conceptually, policy-based methods, directly learning the policy, you would optimize what you care about. On the other hand, for value-based methods, you're indirectly solving the problem because you're first solving your Markov decision process, which is good because it exploits the problem structure. But in some sense, you're indirectly solving for the optimal policy. Empirically, policy-based methods are in practice more compatible with your deep networks. They are more versatile and they're more flexible. And we're also going to see how we can kind of extend these policy-based methods even beyond reinforcement learning to text generation. On the other hand, value-based methods, they're more compatible with exploration, so defining things like Epsilon greedy exploration and off-policy learning, and in particular because they exploit the problem structure of these Markov decision processes. They are more sample efficient when they work. So a bunch of trade-offs between policy-based and value-based methods. So now let's go into detail. How exactly do these policy-based methods work? So we're going to look at this very simple game. This is the Pong game, where this is the opponent, and you're controlling this single paddle. It's just two actions: move up and move down. And the goal is to bounce the ball into the opponent's area, while preventing the opponent from bouncing their ball into the same ball into your area. This is a very simple Pong game. And we're going to see how we can design a policy-based method to solve this. So you've seen that this game operates on raw pixels. We have this pixel which depicts the score of yourself and the opponent. We have the paddles for yourself and the opponent, the positions, and also the ball. Right. So in this case, it's an 80 by 80 height by width image. So we're going to define a model. It can be a neural network or a convolutional model with some hidden layers with parameters theta that predicts the probability of moving up. Again, since there's just two actions, you can just define one neuron, the probability of moving up, and conversely, you have the probability of moving down, which is 1 minus that action. And we know that in this game, if you successfully bounce your ball over, you get a reward of +1. And otherwise, if the ball gets bounced by the opponent across your side, then you get a score of -1. And then the goal is, how can we actually learn this set of parameters theta that prescribes a good sequence of actions to actually allow us to consistently score points? So now suppose for simplicity that we had these training labels. So in other words, given all these states x1, x2, x3, we knew what we should do. So in other words, we could maybe get a human to play this game, a human expert, and for all these states, it will give you the perfect sequence of actions to get this reward. Then you would probably treat this learning problem as a supervised learning problem. So you're given some inputs, and you're given these targets, whether you should move up and down, as given by a human expert. And what you would try to do is to maximize the log probability of the correct action given your state. So this is simply your cross entropy loss, and you would do an average over your sample, your data points. That would be your objective function, and you will kind of solve that using gradient-based methods. That's if you knew the training labels for every state. But of course, the main issue here is that we don't have labels. We don't want, or we don't have a human expert labeling it for us. So the question is, should we actually go up and down? What should these training labels be? So let's just try and act according to our current policy. So this model defines a policy, which is a probability of up and down given state. So just given this policy, I'm gonna follow it. So maybe at the initial state, it outputs a higher probability of moving up, and then after sampling from it, you actually move up, and that gives you into a new state. And given this new state, I'm gonna put it back into the current model, and the model describes a current policy that maybe tells me to move up, and then you probably move up again, and then move down, move up across your sequence of states as prescribed by your current policy. If you recall, this sequence of state and actions as defined by your current policy is called a trajectory. So after a long term of playing, obviously we have this sparse reward problem in reinforcement learning, so we don't get reward signals every time step. But across a sequence, maybe we finally observe some reward. So maybe after the sequence of 6 steps, you are able to bounce the ball over to your opponent's side and you win. So you get a +1 reward. And I'm just going to keep doing this. So for certain start states, I'm going to use my current policy. I'm going to win at the end. Maybe for a certain, and then I'm going to reset my start state. I'm going to follow the policy again, and it ends quicker because I lost. And maybe for another one I lost, and then for the 4th one I won. So I can collect many of these rollouts given my current policy. So using these rollouts, what can I do? So we know that in this sequence of actions, we don't exactly know what we did well, but we know that apparently it was something good because we got a positive reward. And likewise for this one. And on the other hand, for this sequence of actions that we've been taking given our policy from the initial start states, we don't know what we did, but we know that it was bad because we lost. So what we're going to do is just to pretend that every action, we're going to give equal credit to each of these actions that we've taken across this trajectory where we've won. And for each of these actions, I'm just going to maximize the log probability of taking those actions again when I see those same states. Because I know that those are good actions that having taken them in the past, I was able to see positive rewards. And on the other hand, for this sequence of actions, which I eventually lost, I'm gonna think that these actions are bad because from these states I take these actions and they eventually led me to a -1 reward. So I'm gonna try to decrease the probability of taking these actions in the future. So in other words, I will maximize -1 times the log probability of taking those rewards, taking those actions from those states. So this is quite intuitive, right? And because we want to work in this reinforcement learning setting, again, we're going to incorporate this discounted rewards. So in other words, I'm going to discount rewards into the past. So at this point, if I see a reward of -1, then this immediate action that I just took, you will scale it by -1. But previous actions, I'm going to discount it by your gamma. So one of them will be -0.9, and then -0.81, and before that. So this will just very simply modify our objective function. Again, you're gonna try to optimize for your log probability of taking those actions given some states. But now the rewards are scaled, either +1 or -1, scaled by your discount factors. So this presents a very simple algorithm, right? You're defining a policy pi that takes in states, goes through some parameters theta, and outputs your actions. And you initialize your policy network at random. So initially your parameters for your model are random. Now I'm going to repeat by taking a bunch of rollouts with respect to this policy. So using this policy, I'm going to sample a bunch of these actions and see what states I end up in and what rewards I eventually obtain. And we know that for some of these rollouts, you're going to get a good sequence of rewards with high rewards. And for some of these rollouts, you're going to get a bad sequence of actions that give you negative rewards. And given all these actions that I've taken, all these rewards that I've obtained, I'm just going to increase the probability of actions that have worked well with high reward. So maximize the log probabilities of all these actions with some discount factor. And for all of these that I've lost, I'm going to try to downplay the log probabilities of these actions by multiplying your objective by -1 and some discount factor. So this presents a very simple algorithm. Again, over here, you want to use an epsilon greedy method. So again, that's epsilon greedy from the lecture before, which is instead of just always following, taking action sample from your current policy, you want to also save a probability epsilon of exploring for random actions. And what are some benefits? So it does not require transition probabilities. So nowhere here have we actually derived our Q stars or V stars, our optimality equation that involve these transition probabilities and our expectations. And it predicts the policy directly. So this is actually a very simple algorithm. And you'll probably think, after all the trouble that we did, in deriving your Q stars and V stars from last lecture, it will actually be a surprise if this actually worked well, right? But in practice, it actually does. So, after training it for a bit, you can actually, so this is the opponent, this is you. It's very jumpy because at every time step, you're making a bunch of actions up and down. And you see, after training for a bit, it actually works really well. It's able to quite consistently beat the opponent. Yeah, you get a point. So then the question is, such a simple algorithm, why does this work? And if it really works so well, why did we go through all the trouble of deriving our value and policy iteration methods from Tuesday's lecture? And if it does work, under what scenarios does it work, and under what scenarios are there possible drawbacks to this method? So we're going to look at this method in more detail, and we're going to see, whether we can actually, give some guarantees for why such an objective function would actually work in reinforcement learning. So let's look at this. So I'm going to first start by defining a class of parametrized policies. So for each policy pi, it's associated with some set of weight parameters. So again, you can think of this as, if you're defining a neural network that takes in states, goes through some parameters data and outputs some actions, you will have this set of all your neural networks, each of them with one particular set of weight parameters. Some are obviously good, some are obviously, random and bad. So for each policy, I'm going to define its value. And what this value would be is, condition on this particular policy pi with parameters data, the expected long-term reward by taking this policy in this environment. So again, this long-term reward would, take time steps from 0 all the way to your horizon. And for each time step, you'll observe a reward and you would discount it by gamma. So that's the value of each policy. And so according to this value, some values of theta, some set of parameters will give you a really good policy that consistently gives you really high expected reward over your long term. And some policies will give you very bad reward and just never really gets any reward. So we're also going to define two things. We're going to, again, revisit this in terms of trajectories. So trajectories are, starting from some state, taking actions, observing rewards, and going to next states. So I'm also going to write out the probability of each of these trajectories. So the probability of a trajectory is given by a couple of things. First of all, if you're in some start state, your policy, pi, with current value of your parameters theta, will define what probability of taking action A0 that your agent will currently take. And once you choose a probability of taking action A0, you would then have to give it to the environment and actually multiply it by the transition probability of going to your particular next state S1. And then once you're in S1, you're again going to reevaluate your policy with S1 as input and predict a probability of taking action A1. And likewise, given S1 and A1, you will multiply it by the transition probabilities that it goes to S2. So all this sequence of multiplications up until your horizon, that is equal to the probability of a particular trajectory. And likewise, I'm also going to define the reward of these trajectories, which is very simple. It just takes in all these rewards and sums them after multiplying by your discount factor to the power of t. So given these two things, I can write the reward for a particular policy with parameters theta as, instead of the expectation of your rewards under this policy, I can write it as the expectation under trajectories sampled by your probability distribution over all trajectories under your policy pi times the reward of each particular trajectory. So to see how these are equal, so obviously, inside the expectation, this, summation of rewards scaled by your discount factor is exactly your reward of a trajectory. And my expectations under a policy are exactly an expectation under the distribution of trajectories, because for each trajectory, you're actually following your policy pi and taking actions as described by what my policy should be. So these two are exactly equal. So then the goal is, we can write the value of these policies. And the goal is to find the optimal policy theta star. And we know that the optimal policy would simply be an argmax over all values of your parameters, J of theta, which is the long-term expected reward under this policy. So this is a maximization problem. A general method to solve these maximization problems would definitely just be, taking a gradient and doing gradient ascent because you want to maximize. And you would take gradient with respect to your policy parameter theta. So how can we do this gradient ascent? So we know that the expected reward is equals to the expectation under trajectories sampled from the distribution of trajectories given by your current policy, the reward of your trajectories, right? I'm going to write that as an integral over trajectories, tau. And I'm going to try to differentiate this by taking the gradient with respect to J of theta, the gradient of theta with respect to J of theta. So I can move my gradient with respect to theta inside the integral because the reward of trajectories doesn't depend on theta. And if you recall, the probability of a trajectory is equals to the product of all of these terms. So starting from initial state, looking at what actions your policy tells you to do, and all these transition probabilities. So taking gradient of this really this huge bunch of multiplicative terms is intractable, right? You can't even think of how you can do the chain rule for this. So you can't really take a gradient of this with respect to theta. But there's some tricks we can do. So one trick we're going to do is that we're going to rewrite the gradient of your probability of trajectories with respect to theta. I'm going to multiply both the numerator and denominator by the probability of your trajectories, right? So these two cancel to be 1. So this doesn't really change anything. And then we also know that the gradient of a term divided by the term itself is equals to the gradient of log of the term, right? This is just by calculus. So in other words, we've converted the gradient with respect to your probability of trajectories as, first of all, the probability of trajectory multiplied by the gradient with respect to log of your probability of your trajectories. So now putting this back inside, we're going to again get this integral over your trajectories, the reward of a single trajectory, and now this term, which is the gradient with respect to the log of the probabilities times the probability of the trajectory itself. And we know that this integral of tau, p of tau d tau, is exactly an expectation of your trajectories. Right? I can rewrite this as an expectation. And what's left inside the term of your expectation is the reward of your trajectories times the gradient of the log probabilities of your trajectories. So why is this more tractable? So let's see why in a minute. So again, we know that the probability of trajectories is equal to this really huge product of many terms given by your policy and your transitions. So we know that we are going to end up taking a gradient of the log of these probabilities. So you take log, the product becomes a sum, multiplication becomes log addition. You get this. And taking the gradient with respect to theta, one very nice property emerges, which is that the log probabilities of your transitions actually don't depend on theta. That's some unknown that's just given to us by the environment. So this term actually goes away. And all that's left is a summation over your time steps, the gradient with respect to theta, all the log probabilities of each of the actions taken at each time step as given by your policy. So we've now removed the dependence on your transition probabilities, which is really good for us because that was one big thing we had to deal with on Tuesday. And therefore, the gradient with respect to the reward of each policy is exactly equals to, it can exactly be approximated in this way. So replace this expectation with just samples. And for each of these sample, I'm going to sample some trajectories. I'm going to evaluate the reward of that trajectory. And I'm also going to compute the gradient with respect to each of the actions taken in that trajectory under my policy. So this gives us a very easy way of computing the gradient with respect to this reward, the gradient with respect to theta. Again, the benefits here are that all these terms are easy to compute, right? You can collect a bunch of trajectories from the environment under your current policy. I can evaluate the rewards of these trajectories. That's already given to me by the environment. That's just a sum of my long-term discounted rewards. And again, for each particular sequence of states and actions within this trajectory, I have a model that computes the probability of a particular action given that state. And the good thing is that we now no longer depend on these transition probabilities. So what is the interpretation of this gradient estimator? So it's very similar to the method of Pong that we looked at just now. If the reward of a trajectory, if R of tau is high, I'm going to push up the probabilities of all the actions seen that allowed me to obtain this trajectory. So that will be increasing. This will be high and positive. I'm going to increase the log probabilities of all the actions under this trajectory. And conversely, if the reward of my trajectory is low, so if this is high and negative, then I'm going to push down the log probabilities of all the actions seen under this trajectory, which was exactly what we saw in Pong, right? We sampled a bunch of trajectories. We don't know what happened in the middle, but we obtain a reward at the end. So for all of these actions in the middle, so for all the summation over your t from 0 all the way to when you finished, I'm going to try to maximize the log probabilities with scale by positive reward, +1. And for these, I would kind of scale each of these by -1, so to decrease the probabilities of taking these actions that led to you losing. So these are actually the same. The intuitive algorithm that we derived for playing Pong is actually exactly the same as the gradient estimator that we saw was derived exactly. And that actually gives us a very nice algorithm. This is called the reinforced algorithm. It's also known as policy gradients. What you're going to do here is that you're going to start by initializing a differentiable policy pi of a given s with parameterized by some parameters theta. Again, you want it to be differentiable so that you can actually take gradients with respect to theta to update your policy weights theta. And you're just going to forever repeat by generating an episode. Again, this episode, which is your sequence of states, actions, rewards, next states. This is exactly your trajectory. You try to sample these trajectories given your current value of the policies pi. And for each step of the episode, I'm going to look at the cumulative return. And I'm just going to update my parameters using this update rule, which is the cumulative return times the gradients of the log probabilities of the action that you just took. And that will give me a rule to compute the gradients with respect to theta, and therefore update theta to get a better set of policy weights and a better policy. Again, when we say sample an episode or sample a trajectory according to your current policy, you want to do something that's epsilon greedy. So with 1 minus epsilon, follow the current version of your policy pi. And with epsilon probability, you would just want to sample randomly so that you explore the environment. And this epsilon should start really high. So at the start, when your policy is rubbish, you would just do all exploration. And slowly, as you get a better policy, you will also follow your policy more rather than exploring. So this seems a very simplistic method, right? I think the main issue here is that was saying that this trajectory can occur over a very long term, maybe 1,000 time steps before you actually observe a reward. So it's very simplistic to say that if this whole trajectory over 1,000 time steps ends up being good, then all of the 1,000 actions were good. So that doesn't seem ideal, right? It seems like if you did a sequence of 1,000 actions, maybe some of them were bad and only some of them were good, that actually led to a high positive reward. Although it's simplistic by an expectation and we do enough samples, it actually averages out and it actually gives you a very good, decent estimator to get a good policy. But again, that requires many samples, right? So again, if you looked at the slide we saw previously, all learning your Q stars and your V stars and all the methods we saw on Tuesday's lecture, they are much more sample efficient. On all these policy gradients, if they actually work, they're more sample inefficient and requires more samples. And requiring more samples also means that if you have very few samples, you're going to suffer from high variance. So how can we actually do better? There's a couple of tricks. One very important trick is that called variance reduction. So the idea here is that if you're actually observing these trajectories, the raw reward is actually not that meaningful. So if all the rewards across this trajectory are positive, if most of the rewards that you obtain from the environment are positive, you're going to keep pushing up probabilities of all actions. And that's not going to be very meaningful for your policy. So instead of the raw reward, what's more important is that whether the current reward you're obtaining is higher or lower than what you normally expect to get. So that at least gives you a sense of whether your policy of this particular action is in a step in the right or wrong direction. So therefore, a very simple extension is to introduce a baseline function that kind of scales this reward by a particular baseline. So this baseline should probably track like something like the moving average of all the rewards. So that gives you what these the normal expectation of rewards you should get is. And therefore you see in future rewards you want to compare whether these rewards are higher or lower than a baseline. And again, you can show that it provably reduces the variance of this estimator while also remaining an unbiased estimation of your gradient. So this variance reduction with a baseline is very important. And usually these baselines are very simple. Just an exponential moving average of the rewards can give you a big boost in performance. But we can also do better than that. Instead of just keeping a exponential moving average, which seems very simplistic, what we can also do is, I want to push up the probability of an action at a particular state if this action is better than the expected value of what we should get from that state. So in this case, the expected value of what we should get from that state should remind you of one thing, which is actually the state value function. So we call the state value function exactly computes, given this particular state and following either a policy or an optimal policy, what is the expected long-term reward that this state should give me. And on the other hand, your Q function, which is your Q essays, that will tell you if I'm from a particular state and I take a particular action under a policy or under the optimal policy, what is the expected long-term reward I get. So in other words, this QSA minus V of S exactly tells us what is the difference between taking this action, the benefit of taking this action with respect to my long-term expected rewards. So then if QSA minus V of S is large, then I should be happy by taking this action A. Otherwise, if it's small or even negative, then we should be unhappy with this action. So using this, we actually get a better estimator, which is that I'm going to scale it not by the raw term, the raw reward, or even reward minus the baseline. I'm going to compute the expected utility of taking this particular action from my state. So that'll be my QSA is minus V of S as evaluated by the current policy pi. So this actually presents our next method, which is actually a combination of Tuesday's algorithm and today's algorithm. So on Tuesday, we know that at the start, you don't know these Qs and Vs. So right, and Tuesday we presented some methods to learn them. So we can use Q learning or any of these deep Q networks to actually learn these Qs and Vs. And the combination of these methods is actually called actor-critic methods. They combine policy gradients and Q learning. Why is that? They will train two things. So they'll train an actor. An actor will be the one that outputs a policy. So in this case, given a particular state, you're gonna maybe start sharing some layers, and you're gonna then branch out. On one side, you're going to predict a policy, which is a distribution over your possible actions to take. And at the same time, I'm also gonna predict a value function, which is the value, my Q, of a particular state and a particular action. So again, you can, these are called actor-critic methods because the policy is the actor that tells you how I should act. And the critic is the value function. The critic, which is a Q function, is one that evaluates how good the states and actions currently are. So how would you train these jointly? So for the critic, the one that estimates the Q values, we've actually seen from Tuesday's lecture that we can actually train it using deep Q learning. So again, we derive these Bellman optimality equations. We know that the Qs at optimality should have this term, the Q learning target, and the output from the Q network being exactly the same. So if that happens to optimality, what I can then do is compute the difference and try to minimize that to 0. So that would be how you train your value function, your critic. And at the same time, you will also train your actor, which is the one that actually outputs a policy and tells you which actions to take. So what is the objective function for training the actor? Again, that would be the objective that we just derived, which is that the gradient of J theta, which is how good a particular policy is. You're going to take gradients with respect to theta, and that's equals to the advantage, which is how good this action was. And how good the action was is actually given by the critic. So right, you use the critic to at a given state compute what is the value of taking action at that state, and this value will be your long-term cumulative rewards as estimated by your Q values, and you will subtract the baseline value of that state, which is an average over all possible actions. So this difference will tell you the difference in expected rewards by taking this particular action, and you will try to scale that by the log probability of taking that action. So if this is high, you will push up the value of that action, and you will try to take it more in the future. And conversely, if this is small or negative, you would decrease the log probability of taking that action in the future. Cool. So these are called actor-critic methods. Combining critics that evaluate the state and action value functions with actors, which actually tell you what actions to take. And I guess most of the methods, I think nowadays, these actor-critic methods are very strong baselines for many reinforcement learning problems. They're also kind of these like go-to baselines if you have a discrete set of actions that you want to take. And again, you want to use some of the tricks we saw in the previous lecture, which is that you want to use sufficient exploration. So at the start, your policies are bad, so you want to do sufficient exploration so as to actually get trajectories with actions that give you high rewards. You also want to, as you're doing exploration, you want to keep an experience replay, which is to remember some of the sequences of states and actions that you've taken and store it. And when you're doing these gradient updates, in both for the critic and for the actor, you want to sample a batch from your experience replay. You want to shuffle it, you want to sample a random batch. So you're actually decorrelating these samples. And likewise, you want to use fixed targets. So again, you want to use W minus. a previous set of parameters to give you your Q-learning target while updating W for your predictions. And then maybe after a few thousand epochs, you would replace your W minus with the current value of W. So this fixed targets prevents the issue of non-stationary targets. Awesome. So that is the main, at least from the algorithm side, those are the main, at least are the main introduction to the different types of algorithms used in reinforcement learning. So just to summarize real quick, we looked at value-based methods. So these value-based methods, we started by looking at these MDPs, which formalize the reinforcement learning problem. We looked at important values, our Qs and Vs, and we derived these Bellman optimality equations. And then we showed how to obtain the optimal values of Qs and Vs using value iteration, policy iteration, tabular Q-learning, and the extension to deep Q-learning. So the benefits here is that you're using the structure of MDPs, and therefore they're more sample efficient. But the main problem is that after learning these Qs and Vs, you then have to rederive a policy, which might be difficult if your actions are high dimensional and you can't really take argmax over your actions. On the other hand, in today's lecture, we've actually looked at more policy-based methods. So instead of using these value functions, your Qs and Vs, you will try to estimate your policy directly to just define a model that takes in states and predicts your actions. So that's your policy. And you will update this using a policy gradient method, which is the gradient estimation that we just looked. So the benefit here is that you're directly learning the policy. You don't have to go through all this trouble of learning your Qs and Vs and then deriving a policy. But the issue here is that because you're not really leveraging any structure in the problem in these MDPs, you are most likely going to be less sample efficient. And we also looked at how we can combine these methods using actor-critic approaches, where you have an actor that using policy gradients predicts a policy. And at the same time, we have a critic, which predicts these Q values that tells you, how good each of the actions you are taking are. So instead of actually just using the rewards or rewards minus a baseline, you will use the critic to estimate how good these actions are. So that's kind of in the middle, these actor-critic methods. So now we're going to look at some applications. We'll look at two sets of applications. Last week I just went very quickly using. I went very quickly through language and reinforcement learning. Today we're going to look at another set of applications which uses Rrl to do stochastic optimization, and this will be very useful in kind of optimizing over your discrete tokens, like you need to do in text generation. So we're going to look at stochastic optimization. So what is this area of stochastic optimization? So here's a very general optimization function. I'm going to take a max with respect to some parameters phi. And what am I going to take the max of? I'm going to take an expectation with respect to some distribution of z, and this distribution of z actually depends on phi. And once you're able to sample some values of z from this distribution of z, you're going to evaluate f of z, which actually tells you how good each of these z's are. So why did I give you this problem? Well, this is a very general problem setup that we actually saw before. We actually saw this in VAEs. So if you recall what we had in VAEs, we started by deriving this evidence lower bound, right? And in this case, the evidence lower bound depends on x and also depends on two parameters, theta and phi. So what are these two parameters? So again, given x, you actually have two sets of models, an inference model, Q of phi, that takes in x and predicts a distribution over z's. So x is your input data, z is your unobserved latent variables. The inference model takes in your observed input data x and outputs a distribution over z's, your q phi z given x. And then we saw that you have to sample a new set of z's before you can actually put it back into the generative model. So the generative model would take in z's and use a generator p with respect to theta, parameter theta, that actually takes in z's and outputs a distribution over your real data x. Right? This sort of was a VAE formulation that we looked at last Thursday. So we saw that the goal, which was to maximize this evidence lower bound, can be rewritten as an expectation under the inference model, the log likelihood of predicting your real data under the generative model, minus this KL term, which encourages the distribution of your latent variables to be close to your prior. So I'm going to ignore this KL term for now and just focus on this part, this optimization problem. So this and this actually share many similarities. So if you recall for VAEs, we know that the gradient with respect to theta is very easy to do, right? Once you have sample Z, you're going to put parameters theta and predict your X and maybe define your log likelihood or your mean square error. And that is directly differentiable with respect to theta. So the generative model is very easy to learn. The difficulty was in learning the inference model. Why is that? Because in the inference model, you have an expectation under the inference model, expectation of under the samples from this inference model, and some term that further depends on Z. And you want to be able to take gradients all the way back, all the way from the outputs of Z through Z and through the parameters of the inference model that generated this distribution over Z. And why was that difficult? We saw that one option was to take in your inference model from X through parameters phi, get a distribution over Z, and then sample Z from this distribution, and then continue on with your computation. But once you start sampling Z, the issue is that you have this this random sample that you can no longer backpropagate through to the parameters phi that output your distribution over Z. Right? This is a stochastic bottleneck, this random node over here. So we saw how to kind of get around this problem by reparametrization. So instead of sampling Z from the distribution as given by the inference model, what you should do instead is to just sample epsilon, a noise vector, and then do a linear transformation of this epsilon using the mean and variance parameters as given by Q of Z. So what you will get is that the randomness is now within this epsilon, and your Z would now be deterministic, so that your Z can actually go on to further computations to actually reconstruct X, and all these loss functions can now backpropagate with respect to Z, which is deterministic, and backpropagate with respect to phi, which are the parameters that generated the mean and variance of your Q of Z. Right. So all of this was back in the VAE lecture last Thursday. So we look at the similarities here. Again, theta was easy. The main similarities is in optimizing for phi. You actually do exactly get this formulation, right? You're taking an expectation under Q, which depends on phi, that actually defines the distribution over Z, from which you have to do some sampling. And then the sampled Z then goes through some computation. And that's why we call it stochastic optimization, because in this computation graph, there's a part where you actually have to sample certain layers or certain variables before these variables can then define your reward. That's why we call this stochastic optimization. So now that we've seen this general stochastic optimization problem encapsulates VAEs, and we saw that we can actually solve, at least in the VAE case, by reparametrization. But what are some requirements that we can actually get it to solve via reparametrization? There are a few. So we first have to require that Z is continuous. Why is that? So once Z is continuous, then you can actually go through computation afterwards to compute your loss function, and then compute the loss of your the gradient of your loss with respect to Z, right? These gradients are only well defined if Z is continuous. And in the case of VAEs, Z is continuous because your Q of phi defined a Gaussian, and then Z was a continuous sample from this Gaussian. So Z is continuous. We have that in VAEs. What we also have is that Q of Z is reparametrizable, and we saw that as well. We saw that instead of sampling Z from the distribution as given by the latents, we could instead sample a noise vector from just standard Gaussian noise, and then obtain a deterministic Z using a linear transformation of this noise. And this linear transformation would be by the mean and variance parameters as output by your inference model. So at least in the case of VAEs, our Q of Z was reparametrizable. So we could move the randomness into epsilon and have Z deterministic, and you could backpropagate gradients through Z and to phi. Something else we needed was that f of Z, which is all the computation function that goes on after Z, that is also differentiable with respect to phi. And in the case of VAEs, we do, because once you sample a discrete Z through reparametrization, It just goes through a bunch of neural network layers to get your output and define your loss. So all of this is also differentiable with respect to phi. So these are some requirements. And now let's look at reinforcement learning. So in reinforcement learning, we actually have a very, very similar setup, right? If you look at what we derived in the first half of the lecture, we looked at all this set of parametrized policies, with policies that take in states and go through some set of parameters phi to predict actions. And we looked at the expected reward of all these policies, right? That's a function of your parameters phi. And we saw how we could rewrite this as, again, a maximization problem of my policy parameters phi, an expectation of trajectories sampled from this set of from this particular policy, times an expectation of the reward of these trajectories, right? So this was the exact reinforcement learning problem that we had, which we then derived policy gradients. So what is happening here? So first observe that this and this is again under the same formulation. You're maximizing over some parameters. You have an expectation in which you have to actually take samples from a distribution. That's why we call it stochastic optimization. And the distribution actually depends on the parameters phi. So again, the big issue here is that once you take samples from this distribution, and then your reward is only defined on these samples, how can you actually backpropagate this reward through your stochastic sampling process and with respect to phi? So what is different from reinforcement learning? Why can't we use reparametrization? So in Rrl, at least what we've seen for this set of discrete actions, instead of z being continuous, our trajectories are now a sequence of discrete actions. Given state, some set of discrete actions that you take. So we no longer have this this property where the things that you're sampling are continuous, which is kind of bad. Another big issue is the probability of your trajectories given your current policy is also not reparametrizable, and that follows from the same argument that now T is a set of discrete actions. So your P, which is basically your policy, that's going to output a multinomial over your possible actions. That is not reparametrizable like how Gaussians are. So that's also a big issue. And lastly, once you get your states, you're going to go through a policy to get actions. So a sequence of actions to your trajectory. When you go from trajectory to rewards, instead of having these decoder layers that you did in variational autoencoders, now you just have a black box function, right? Why is it a black box function? Because you have all these actions that your agent is taking. You're going to give it to the environment. This environment is a black box. We don't have a parameterized function for the environment that we can differentiate with respect to. And now this environment is just going to spit me out some reward. So this dotted line question mark here basically means that this reward is a black box function with respect to your actions. So then that gives you it's almost impossible to take gradients of your reward with respect to your actions or with respect to the policy parameters phi. So although both of these fall under the same framework of stochastic optimization, we've seen that there's some conditions that, if met, we can actually solve stochastic optimization through reparametrization. But at least in the case of Rrl, because of discreteness and because of this black box function that produces the rewards, we can no longer do this. And what we've actually seen reinforce our policy gradients is actually a very general purpose solution to solving for these stochastic optimization problems. So recall what we did in reinforce was that, given this problem, we want to take gradients with respect to phi. We show that a gradient with respect to phi can be written as something like this. This is the exact equation that we derived, which is an expectation under distributions from your Q, f of z, which is the reward of a particular trajectory, scaled by the gradient with respect to log probabilities of that sample. So that's exactly what we derived when we did policy gradients, right? We're gonna, take scale it by the rewards of a trajectory and the log probabilities of taking those actions, right? So in this case, our policies basically corresponds to this Q of phi. Our rewards correspond to our f of z, and you're maximizing what parameters phi, or in this case, theta. So reinforce, as what we've derived, is a very general way of taking gradients with respect to these stochastic optimization problems. And once you take gradient, you can actually compute a Monte Carlo estimate. So instead of taking true expectation over your Q of z's, which is difficult, what you can do is just sample a bunch of the z's. So sample a bunch, and for each of the z's, compute f of z, and then also evaluate the gradient with respect to the log probability of picking that particular z. And then I'm going to take an average over a bunch of z's. So by replacing the expectation with respect to an average. And that's exactly what we've seen, right? In this case, the z's are trajectories. I'm going to sample a bunch of trajectories. In this case, it's one sample, one trajectory, but you can, to do an estimate, you would take a sample over a bunch of trajectories. And for each of these trajectories, you would compute the reward, which is your f of z's, and then a gradient of taking all of the actions in that trajectory. So the reinforced estimator, as we've derived, is a very general estimator for these stochastic optimization problems. And the good things are that we just need a distribution Q to allow for easy sampling. As long as you can sample all these z's, you're good. So that means my z can be discrete or continuous, right? In our case, our z's, which is trajectories, they are actually discrete actions being sampled at each time step. So z can be discrete or continuous. Q of z, which is the distribution the distribution over your z's, or in our case, the distribution over trajectories, can also be discrete or continuous. In our case, our Q of z was basically our policy pi, right? That take in states and outputs a bunch of actions, a distribution over actions, but then you have to sample an action before you compute the reward of those actions, and therefore the reward of the trajectory. So the Q of z's can be both discrete and continuous. One thing that it must be is that it must be differentiable with respect to phi. So obviously, in our case, our parameters, our policy is parameterized by theta, and you must be able to take gradients with respect to theta of the policy. So that is very easily achievable. But a good thing is that Q of z can be discrete or continuous. And the other good thing is that your f of z can be a black box, right? You no longer need something like a decoder that had gradients with respect to, like in VAEs, but now your f of z's, or in our case, the reward of these trajectories, it can be just any arbitrary black box that you give it a trajectory, and the environment would return you some reward. You just need to be able to query it. You don't need to know what's actually inside. It can just be a black box that you can query. So the reinforced estimator for stochastic optimization has all of these benefits. So we've seen these benefits in the case of reinforcement learning. We had some discreteness in our actions. We had this black box reward function given by the environment. But what are some other important applications of using reinforce? And that will be in text generation. So in text generation, if you want to define these generative models like GANs for text generation, one big issue is that text data is indeed discrete, right? So in this case, you have true data from the real world. So again, if you recall, GANs have this generator that generates text, and you also have a discriminator that takes in real text from the real world and the text that you generate, and you will try to distinguish between these, right? And then you would play a minimax game between the generator and the discriminator. So text data, both from the real world and also what you generate, they will be discrete. So you can think of, your generator will be some LSTM or transformer that outputs probabilities of words at each time step. And then you will need to sample these words to actually get a sentence. And once you get a sentence, you will compare it with some real sentence from real world data. And your discriminator will try to give you a signal of how close or how different these two sentences would be. So that's one main issue. And therefore, this discriminator gradient does not exist, because once you start sampling these words, you can no longer take gradient with respect to what you had before sampling. So how can you do this? So here, I think here's one of the early papers called sequence scan, which is a sequence generative adversarial networks. And what it did exactly was to build a generator and discriminator for text generation. So what the generator was given a particular words, maybe given 3 words generated so far, your generator would be some language model that would then define next words to generate. So the words to generate will be your next actions. And you will do some search. It's not really important what this search is, but you can just think of it as an efficient search strategy for the most likely sentence. Because if you want to generate a sentence of 10 words and you've generated 3 words so far, you actually have to possibly search over all vocabulary size to the power of 7 next words in order to get the true argmax of your sequence, right? So you can do some, simple heuristics, like you can do, local maximums at every time step, or you can do something in the middle, which is what they're doing, called a Monte Carlo search. But that's not super important. Just know that, the generator will take in some words and it will try to predict the next words to generate, so that you can actually sample an entire sentence from the generator. So once you sample an entire sentence, you want to apply this discriminator on either real sentences or the sentences that you have generated. And if they're similar, so if what you generated is similar to real text, you should give a high reward to your generator, and otherwise you should give a low reward to your generator. So what would you do now? So again, it's not differentiable, but you can apply these policy gradient methods. So what you would do is you would sample your z1s to zk's. So what these are would be, each of these z's would be complete sentences as output by the generator that you have sampled from the generator. And the generator will define a distribution over your z's, right? So that will be your language model. And after you've sampled all of these complete sentences, what you would like to do is you would like to compute gradients with respect to phi, which are the parameters of your language model, your generator, of the expectation under the sampled sentences or a distribution of sentences, and the reward of each of these sentences. And we saw that using policy gradients, we could approximate it using a Monte Carlo sample. Sample a bunch of complete sentences. For each of these complete sentences, my reward will be given by the discriminator reward. So how close it is to real text. And you will multiply this by the gradients of the language model with respect to language model parameters, the likelihood of generating each of these sentences. So again, the intuition here is that, for some of these generated sentences, they're going to look like garbage. So the discriminator reward is going to be very bad. And then you will want to decrease the log likelihood of generating those sentences of the language model, the generator. And for some of the generated sentences, at the start, just by luck, and eventually as you get a better generator, some of these generated sentences are going to look really good, like real sentences. So that will get high reward, and you will try to push up the probabilities of the generator language model generating those sentences in the future. So so that's the basic application in text generation. And of course, training a discriminator is easy, right? The discriminator, it takes in true data and real and fake data. It will just train a classifier. Everything is differentiable. It's easy. There's no stochastic optimization going on. And of course, there's that was in 2017, and subsequently people have proposed better methods to do this. And there's some issues that, at least in this case, you need to wait for the generator to generate the entire sentence, which might be quite long, before you get a single reward, which really reminds you of this sparse reward problem in reinforcement learning. So what you can do is you can define better discriminators that instead of giving a single feedback after the entire sentence is generated, give partial feedback for prefixes that you're generating. So this subsequent paper defined a discriminator based on recurrent models that compare real prefixes, at every time step generated by the model with real prefixes from real text. So now you get better dense rewards. So again, under this formulation, your samples instead of complete sentences will just be prefixes. Your generator that defines the distribution over the prefixes that you want to generate is again your language model, and you will estimate the gradients with respect to your language model using these Monte Carlo samples that, for every prefix, the discriminator tells you how realistic it is, and you would try to weight up the samples of those that have high reward. Also some things, like using large batch sizes, again, reinforces large variance, and is in general not super sample efficient, so you have to use large batch sizes. You have to subtract your baselines to make the variance lower, and just look at the paper for other tricks that they used. There's also other approaches. If you want to do text generation without actually reinforcement learning, there's also some approaches. I'm not going into too much detail, but I'm linking some references. And just to also go over briefly, what are some other applications? You can also apply this in dialogue. So in dialogue, again, you have a model, Q of phi, that's your generator model for your dialogue across multiple utterances. And you will sample these dialogue. So Each sample will be the input message, a bunch of responses across your dialogue, and your reward. Just because we've looked at these approaches, you can basically define any black box reward function, right? So you're not limited to a discriminator. So any type of reward function, like this paper looked at a bunch of auxiliary rewards, like how easy it is to answer your utterances, information flow across the sentences, how meaningful it is. If you had human data, or you can even get humans to annotate all these black box reward functions, you can use it in place of f of z, right? So as long as any reward function that you can define on your samples, it can be a black box. You don't need to take gradients of it. You can define it here. And even for things like blue scores, again, it requires you to have sampled the text into raw text, into these discrete tokens, and you can kind of compare these sample text to your reference, and you can compute blue score, cider scores. All of these black box evaluation metrics can be used in place of f of z, right? And again, those are not differentiable using standard gradient methods. One is because of the sampling that you have to do to get the text, and also all these blue score things that match n-grams. Those are in general not smooth differentiable functions. So all these can be solved using your policy gradients. Now, just guess one last application, just another few minutes. This last application would be that in using hard attention. So I'm sure most of you have seen soft attention, right? Soft attention is basically outputting an attention map that has gone through a softmax, so its values between 0 and 1. Hard attention, on the other hand, would be a discrete latent variable that you would try to output a probability of it being 0 and probability of it being 1. And you actually want to sample a discrete gate, which is either 0 or 1. Again, once you have this sampling process in the middle of your model, you can no longer backpropagate through it. So you can again use policy gradient methods. So in this case, we're looking at multimodal learning. You have language, visual, acoustic coming in at every time step. You want to use an LSTM to combine all this information. And what we're defining here are these hard attention 0 or 1 gates that basically tells me whether the visual modality at this particular time step is going to be useful. If it is, I should assign it 1 and it will go through, and otherwise I should assign it 0. So this particular time step would have 0 for the visual modality. So again, because I have to define a model that outputs a distribution over 0 and 1 before actually sampling the values 0 and 1, this part here is going to involve a stochastic sample. So you can't backpropagate with respect to these parameters. But what I can do is, again, using these policy gradient methods, my z's here will be my hard attention scores, which are either 0 or 1. My q of z would be this controller, which actually defines the distribution over my zeros or ones. So this would take in the visual input and tell me whether this visual input looks like it's going to be useful or not useful. So it takes in the input and outputs probability that should be 0 and probability that should be 1. And if I want to take gradients with respect to the parameters of this controller, what I need to do is also define a reward function. So for each of these hard attention scores, 0 or 1, I'm going to actually apply it to my data and train a model to tell me how well it's able to classify sentiment and emotions, or whatever task you want to complete. And this classification accuracy can be used as a reward function to tell me how informative, how good my 0 or 1 hard attention choices were. Right? So at the start, my 0 and 1s were random. It's going to mask out important visual features, and it's going to let in useless visual features. So my classification accuracy is not going to be good. So the reward is going to be low, and I'm going to try to push down those probabilities given by the controller. And slowly as I get better, I'm going to be able to accurately mask out useless visual features and let in useful visual features. So now my accuracy is going to be higher, and I'm going to push up these probabilities that gave me these 0 1s. So that's another example. And we find that in the case of sentiment and emotions, it actually rejects non-informative visual features and passes through smiles. And in the case of image captioning, we're given an image. Hard attention also looks at a bird. Correctly looks at a bird, and over a body of water, you look at water. Well, conversely, if you use soft attention, sometimes it looks at the bird, but other times it doesn't really look at anything. So that's it. Let me stop there. For language and Rrl, we talked about these different types of applications previously, but I think all of these are also quite simple. So I will just leave these slides online. But just to summarize real quick, we looked at 3 classes of Rrl methods: value-based, starting from MDPs, solving for our Qs and Vs, using policy and value iteration or Q learning, and then going back to obtain a policy. We've also looked at policy-based methods that throw away these Qs and Vs and directly optimize for a policy. And there's some trade-offs between these 2 methods. So value-based methods are more sample efficient because they leverage the structure of the problem at the MDP. But there are disadvantages that you have to compute all these expectations and argmaxes over your actions, your states, your trajectories, which is difficult. Policy-based methods, they throw away your Qs and Vs, they throw away the trajectories. All they need is just sampling your actions and getting the rewards. But the disadvantage here is that since it's much more general and flexible, it doesn't really exploit the structure of the problem and therefore are more sample inefficient. We also looked at certain types of combinations called actor-critic approaches that trains a policy, which is an actor, and also critic to evaluate how good the states and values that the policy actor is currently in. We looked at more generally, going from policy gradients, a general form of stochastic optimization problem, which is useful for reinforcement learning with its black box reward functions, but also in general for like text generation, where you have to sample discrete tokens, which you cannot normally backpropagate through. So looking at text generation, due to discreteness, black box reward functions such as blue scores or discriminators, you can also use that. And hard attention, so your samples being your attentions and your reward functions being how useful this attention, this gated input is to your prediction problem. And to summarize for like language and Rrl, we've also seen a bunch of applications. I think on Tuesday we talked about things like instruction following. We look at giving external rewards to your model so that you can actually encourage the agent to do better than random exploring. And you can also look at some of these slides, which give you some language as domain knowledge, which kind of annotates text to describe certain objects in the Rrl environments, and also better ways of designing your policies to answer these to follow these instructions. But cool, that's all.